we have to mitigate hole tortuosity and analyze it and know when we need to do something about it. So here's I call it the drill co-equation that was, I call it utilized by industry when I came to work in 1975. Its mean effective hole diameter is equal to the bit OD plus the drill collar OD divided by 2. And so what this means from a practical sense is that that bit can move over until there's something to prevent it from moving over anymore, which in this case, on this drawing, is the drill collar. So that bit can actually move over until the drill collar hits the side of the borehole, unless there's something else to prevent it. So you could have two drilling engineers with two different experience base and two different knowledge. One could be drilling in an area where they run 7-inch casing in a 9 7/8 hole, but using 6.5 drill collars. And if you use this drill co-equation for that circumstance, the bit diameter of a 9 7/8 hole, the drill collar OD divided by 2 is 8.5. This drilling engineer would not have any problems probably running 7-inch casing with a minimum pass-through diameter of 8.5 inches. Probably would never have an instance of problems. Yet drilling engineer number 2, he might be working in deep water or an operation where they run tight clearance, tight casing, and let's say he's running 9 5/8 casing through 11 3/4 casing. If he has a maximum of 10 5/8 OD tools, which is likely what you would have for 11 3/4 casing, and he's utilizing 7 3/4 inch drill collars, then if you use his maximum tool diameter plus his drill collar OD divided by 2, plugging these values into the mean effective hole diameter drill co-equation, you end up with about 9 3/16. That diameter is substantially less than his casing OD, and so therefore, if he does nothing to mitigate hole tortuosity, it's very likely he may get his casing, a portion of his open hole, and then he can't run it anymore because he's got a tight spot in his open hole that's actually smaller than his casing OD. Now there are a couple of ways to mitigate this hole tortuosity that I learned and experienced many years ago. One is to run a packed hole assembly. So we can run a packed hole assembly in our drill string, which a packed hole assembly is a series of drill collars and stabilizers. Now here's a model of a stabilizer which happens to have 3 blades on it, and they are normally made on a drill collar type stock. So this would be the OD of a drill collar, but it has blades on it that are just a little bit less than the casing. The OD of the blades is smaller than the casing ID, so they can go through them. And you put these in your drill string to mimic that your drill collars are as large as the hole size. So it kind of mimics that when you put a packed hole assembly together. So I've got a drawing of a packed hole assembly in which, to drill a well with mud motors, you might have a mud motor and an MWD, and then you would put above that a packed hole assembly, which is what I call stabilizers on both ends of one drill collar, and then you put a pony collar, which is a short drill collar, and a stabilizer above the pony collar. Like I say, this mimics having drill collars which are the same size as the bit size because they're relatively short and they have these stabilizer blades on them. An example of using this, going back to the drill co-equation, when you do this, you end up with using the mathematics saying that the mean effective hole diameter of a packed hole assembly is 12 1/4 plus 12 1/4 divided by 2, which is 12 1/4, because they are very stiff and it prevents this assembly from moving over in the borehole. Another important aspect is these blades are typically about 2 foot long. So if you have a 2 foot long blade and you're drilling at 60 foot per hour, then you are getting your formation exposed by these blades 2 minutes for every foot of rotation. So with 2 minutes of rotation for every foot, it's going to smooth out any irregularities in that well bore that were caused as you drill that well bore. And it's also important to note that rotating this packed hole assembly through your well bore is a lot better than just making a wiper trip with a packed hole assembly after you've drilled the well bore, because this bottom hole assembly can actually bounce around and go through tortuous well paths because it bounces around if you're running it on a wiper trip. But when you rotate it as you drill and you're getting this 2 minutes per foot rotation, it does a much better job. Now there's a new and equally as well tool, it may even be better thought of today, it's been out about 20 years, I guess, a rotary steerable tool. A rotary steerable tool is actually a directional tool that's run right above the bit, in which it has actuated pads on the tool which steer the bit in different directions. So it actually has, I believe most of them have 3 pads on it. So by pushing against the borehole, say to the north and to the east, you can make the well bore go to the southwest. So it has these actuated pads on it, and it actually does extremely well of keeping this bit from moving around and drilling another, having a very smooth well bore. If you want the smoothest well bore probably possible, drilling it with a rotary steerable assembly will give you the smoothest well bore. From all the torque and drag work that I've done in my career, I have found that you can get friction factors if you drill wells with rotary steerable assemblies down in the order of about 0.18 to 0.22 by using a rotary steerable assembly. And that value is actually very close to the coefficient of friction between steel and a borehole using synthetic base muds, which is probably about 0.16 to 0.18. So you can actually get numbers, your friction factor, very close to the coefficient of friction by using a rotary steerable assembly. So I hope this video has been very helpful to understand hole tortuosity and mitigations that you can do to help prevent it from being a problem on your well. And I want to wish all of you drillers out there good luck in mitigating your hole tortuosity. Thank you.